This video is a beginning and an end. It's a beginning because the theorem we'll be proving marked the birth of group theory, one of the main pillars of modern math. It's an end because it's normally introduced at the end of a course in abstract algebra, once all the groundwork has been laid. The theorem we'll be building up to is the following. There is no general formula to solve a polynomial of degree 5 or higher. The reason why it's true boils down to a simple fact in group theory. But to see it, we have to connect polynomials, fields, and groups. So we'll first talk about field extensions, then the Galois group, and then we'll see how they come together to prove our theorem. Let's get cracking. Our first step is to define precisely what we mean when we say a polynomial has no general solution. That definition is made using fields. A field, roughly speaking, is any set where you can add, subtract, multiply, and divide elements. The rational numbers, for example, form a field. Importantly, you can't take square roots. 2 is a rational number, but the square root of 2 isn't. If you want to talk about the square root of 2, you have to extend the rationals to a larger field that contains the square root of 2. We'll define a field called Q adjoin square root of 2 as the smallest field containing Q in the square root of 2. That means that it's closed under the 4 operations, so 1 plus square root of 2 is in the field. So is 4 plus 2/3 the square root of 2, and so on. What if you wanted to take nested roots, like the square root of 2 plus 1 cube rooted? Well, the easiest way to do it would be take Q and then adjoin that number in. But in this video, we're not going to take that route. Instead, we'll first adjoin the square root of 2. Then we'll adjoin the cube root of the square root of 2 plus 1. The key point is that at each step, we only adjoined a root of something that lives in the previous field. We first adjoined this number because it's the square root of something in the field before it. We then adjoined this number because it's the cube root of something living in the field before it. That leads us to the key definition. A polynomial f is solvable by radicals. If starting with the rationals, you can extend the field one step at a time, at each step adjoining a root of something that lives in the previous field, and eventually arrive at a field containing all the roots of the polynomial. An example should clarify. For instance, this polynomial is solvable in radicals. This is because it has roots 1 plus or minus the square root of 2. If we adjoin the square root of 2, Q adjoined root 2 contains both the roots of the polynomial. That means that it's solvable by radicals. In general, the roots of a polynomial may be a very complicated mix of nested radicals. But the point is, if it's solvable by radicals, you can build up the field where the roots live by successively adjoining nth roots to the rational numbers. Our next step is to determine, looking at a polynomial, how do you determine if it's solvable by radicals if you don't know the roots beforehand? To do that, we need some powerful new methods. The main insight of Galois theory is to convert problems about fields into problems about symmetry. We all know what symmetry means intuitively. This square is symmetric about this axis because when you flip it, it looks the same. The key leap is to go from geometric symmetry to algebraic symmetry. Let's say you have a polynomial with 4 roots. Root 2, negative root 2, I, negative I. These roots happen to satisfy these 2 equations. Our question is, can we swap these roots in any way so that these equations still hold? For example, if we swap root 2 and negative root 2, the equations still hold. If we swap I with negative I, the equations also hold. But if we swap root 2 and I, they don't hold anymore. The first 2 cases were a symmetry of the equations. The third case was not a symmetry because the equations didn't hold anymore. It turns out that every single polynomial relation involving these numbers that has rational coefficients, like these ones here, still hold when you swap the roots in these ways. Namely, you can swap root 2 and negative root 2, I and negative I, root 2 and negative root 2, and I with negative I. Or you can do nothing at all. The set of all these permutations is called the Galois group of F, denoted Gal-F. And the reason we care about it is because you can determine whether a polynomial is solvable by radicals by looking at the structure of its Galois group. To see what structure the Galois group needs to have, we'll look at this example of a polynomial that is solvable by radicals, and we'll study what its Galois group looks like. To find the Galois group, we first need to list out all the roots of the polynomial and find all the ways to swap those roots that preserve equations involving those roots. There turn out to be 8 such permutations. This is the Galois group of the polynomial f. To get more insight into its structure, we use the fact that f is solvable by radicals. That is, we'll build up the field where the roots live by adjoining nth roots to the rationals one at a time. And then we'll climb the tower of fields, starting with this one. Now, there's a relation with coefficients in the extended field that the roots satisfy. 4 of our permutations don't preserve this new equation. The new Galois group has shrunk to this. This is called the Galois group of f over the field q adjoin root 2. A nice way to see this is in a group table. This was our original group. This highlighted portion is the group after we extended the field. Now let's adjoin another number, the square root of 3 plus root 2. Then we have another equation that the roots must satisfy. 2 of our permutations don't preserve this new equation, so the Galois group has shrunk to this. This is called the Galois group of f over the field q adjoin root 2 and root 3 plus root 2. In the group table, this is the group we started with. This is the group we had in step 2. This is what we have now. Now we'll extend the field one last time by adding in this element. Then we get this new equation. Now there's only one permutation of the roots that leaves all the equations unchanged, and it's the do-nothing permutation. This is called the Galois group of f over the field q adjoin root 2, root 3 plus root 2, root 3 minus root 2. In the group table, we started here, then got to here, then here, and then just one element. This group has a few very specific patterns that occur only when a polynomial is solvable by radicals. The most obvious one is that you can tile the group into sections of equal size. Actually, you can do better than that. Notice that this square and this square have the same elements, just in a different order. Likewise, this square and this square have the same 4 elements, again in a different order. So if we only care about what elements are in each square, there are only 2 different squares. This is true at each level. In general, if a polynomial is solvable by radicals, the number of tiles is a prime number. Here's an example of such a group. Groups with this property are called solvable groups. Now we're ready to see why the quintic has no general formula. It's a fact that the Galois group of a general polynomial of degree n is Sn, the set of all permutations of n things. Let's see whether this group is solvable. For n equals 2, here's a chain of subgroups. The number in blue is the number of tiles that it makes. It's prime, so this group is solvable. And that's why there's a quadratic formula. For n equals 3, here's a chain of subgroups. These numbers are all prime, so the group is solvable. That's why there's a cubic formula. For n equals 4, the numbers are all prime, so the group is solvable. That's why there's a quartic formula. But for n equals 5, the situation changes dramatically. You start off fine, 2 is a prime number, but then you have 60 different tiles, so the group isn't a solvable group. That's why there isn't a general Quintic formula. For n equals 6, the situation continues. You start off with 2, but then you go to 360, so the group isn't a solvable group, so there's no general formula there either. Same for n equals 7. You start off with 2, but then you get stuck at 2520, which isn't prime. No general formula. In fact, you can prove that for n equals 5 and up, the situation always happens. You always get 2 at the start, but the number you have after is never prime. So that's why for degree 5 and up, there's no general formula. Sn is not solvable for n greater than or equal to 5.